but this is a nice downward sloping curve. How do I tell whether it's exponential decay or not? Now you probably remember this from GCSE. You check to see whether it's got a half-life. So in this case, we're starting with 100 unstable nuclei. So when we half it, we have 50. And we just look to see how long did that take. And on this graph, it took 1 second. So if this is radioactive decay, the half-life is 1 second. So now we look after another 1 second. How much have we got now? Has it been halved again? Yes. So this is looking good. Let's check one more. Remember, half-life is 1 second. So after another 1 second, we should have halved again. And obviously I've drawn it this way. So yes, we have. There we go. Look. So it's exponential decay. Okay, but what if you have a graph like this with a shortened axis, a truncated axis? Now, I've started this time with 1,000 unstable nuclei, but half of that's 500 and it's not on the graph. So what do I do this time? Well, in fact, it doesn't have to be a half. As long as you've got your number decreasing by the same fraction every time in the same time period, then it's exponential decay. So what I do is I say, okay, well, let's go for 1 second. So after 1 second, how many have I got left? 900. Okay, so that means that I haven't gone down by a half, I've gone down to 9/10 of what I had before. Okay, so now we go another second and we say, have I gone down 9/10 again? And because I've drawn it that way, yes, we have. So that's 810 there, which means that 810 is 9/10 of 900. So we've gone down by the same fraction in the same time period. So we always check, probably checking 3 is a good idea, I think. So after another 1 second, have I gone down by 9/10 again? And I want you to use your imagination, and obviously that's 729 there. So yes, I have. 729 is 9/10 of 810. So every time I go forward by 1 second, I'm going down to 9/10 of what I had a second earlier. You don't have to do 1 second, but you've got to do the same time period every time. Do you go down to the same fraction of what you had before? If the answer is yes, then you're looking at an exponential decay curve. And while we're talking about the half-life, this is its symbol. And remember, it's the time it takes for half the radioactive nuclei to decay. And why is that a thing? Well, it results from the decay constant. So each radioactive material has a different decay constant, and so it also has a different half-life. You can prove this formula after, I think, video 4 will be able to prove this formula. But now here's a question. Okay, so if the half-life is ln2 over lambda, then lambda needs to be ln2 over the half-life, and there's the half-life there. So that's going to give us a value for the decay constant of 1.1 times 10 to the minus 4. And if the activity is equal to lambda n, then the initial activity is equal to lambda times the initial number of nuclei. And the initial activity is up there. So we get this. Don't forget that it's mega. Don't forget about the mega, and use your unrounded value. I've written 1.1 there, but I think it was 1.05 or something. Use your unrounded value for there in here.